Hi class, I'm going to go through the gas law notes and practice problems with you on your assignment. Make sure you pull up your Unit 3 Matters and its Interactions Guided Notes Review assignment. I'm going to go through the answers with that through these slides, and then I'm also going to do the practice problem examples listed at the top of your gas laws practice assignment. So here we go. So pressure, number 37. Pressure is the result of a force distributed over an area. The SI unit for pressure is the Pascal, abbreviated capital P, lowercase a, which is number 38. Another unit for pressure that we'll use a lot is atmospheres. You can also sometimes see torr or millimeters of mercury. On your assignment today, we're going to use atmospheres as your unit of pressure. Scientists will often express larger amounts of pressure in kilopascals. 1 kilopascal, or kPa, is equal to 1,000 pascals. Gas particles are, number 39, always bumping into each other and other things. The force of the particles against things they bump into creates pressure. The more frequent the collisions, the greater the pressure of the gases. The speed of the particles and their mass also affect the pressure. Think again about the collisions that produce gas pressure. What changes might affect the pressure of a gas in a container? Factors that affect pressure in an enclosed gas are its, number 40, temperature, its volume, and the number of particles. The particles in the gas can move faster or slower. The gas can move into a larger or smaller container, and you can add gas or remove gas from the container. So let's talk about temperature. This is number 41. If you raise the temperature of a gas, if the volume of the gas and the number of particles are kept constant, it's going to increase the pressure. The constant motion of tires on the highway causes tires in the air and the tires to warm up. So this is an example of temperature. As the temperature rises, the average kinetic energy of the particles in the air increases. With increased kinetic energy, the particles will move faster and collide more often with the inner walls of the tire. The faster moving particles also hit the walls with greater force. The increase in the number of collisions along with the increase in the force of the collision causes an increase in the pressure of the air in the tires. So raising the temperature, keeping the volume and number of particles constant is going to increase the pressure. So for volume, reducing the volume of the gas, if the temperature of the gas and the number of particles are constant, it also increases the pressure. This is number 41. So an example of this, imagine you have a plastic bottle that appears empty. If you twist the cap on the bottle and then squeeze the bottle, what's going to happen? At first, the bottle will give a little, reducing the volume of the bottle, but soon you will feel the pressure from the inside of the bottle, resisting your efforts to further reduce the volume. The pressure you feel as a result of the increased pressure of air trapped inside the bottle. The pressure you feel is a result of the increased pressure of the air trapped inside the bottle. As the volume is decreased, the particles of trapped air collide more often on the walls of the bottle. So reducing the volume, but keeping the temperature of the gas and the number of particles constant is going to also increase the pressure. So number of particles. This is number 43. Increasing the number of particles, if you keep the temperature and the volume constant, will increase the pressure. So you can probably predict what will happen to the pressure when you add more gas to a container. So back to example, think about that tire. Once the tire is inflated, its volume is going to stay fairly constant. Adding more air will increase the pressure inside the tire. The more particles there are in the same volume, the greater the number of collisions and the greater the pressure. At some point, the rubber from which the tire is made will not be strong enough to withstand the increased pressure and the tire will burst. So increasing the number of particles, if you keep temperature and volume the same, is going to increase your pressure. So we're going to talk about 3 gas laws. The first one is Charles' law, and this is the chart on number 44. So your description of Charles' law says that the volume of a gas is directly proportional to its temperature in kelvins if the pressure and number of particles of gas are constant. So your real-life example of Charles' law is if we use a helium balloon. So you fill a helium balloon in a warm or hot room and then take it into a cold room. It's going to shrink up and look like it's lost some of the air inside. But if you take it back to the warm or hot place, it fills back up and seems to be full again. So now we're going to talk about the formula for Charles' law. So Charles' law can be written as a mathematical expression where you have V1 over T1 equals V2 over T2. V1 and T1 stand for volume 1 and temperature 1, or your initial volume and temperature before a change occurs. V2 and T2 stand for volume 2, temperature 2, and this is going to be the volume and temperature after a change occurs. Your temperature has to be expressed in kelvins. If temperatures are in degrees Celsius, you cannot use the formula. You're going to get the wrong answer. It's going to do something funky. So to convert Celsius to Kelvin, which is number 45, you're going to do degrees Celsius plus 273. So back up to that chart on number 44 again. Let's talk about Boyle's law. Boyle's law description states that the volume of a gas is inversely proportional to its pressure if the temperature and the number of particles are constant. So the formula for this one is P1 times V1, pressure 1 times volume 1. So your initial pressure and volume equals your P2 times V2, or pressure 2 times volume 2. So this is the pressure and volume after a change has occurred. An example, your real life example of Boyle's law is, again, with a balloon. So air is blown into a balloon and the pressure of the air pushes on the rubber, making the balloon expand. If you squeeze one end of the balloon, it's going to make the volume smaller in that one part, but the pressure inside will be increased, making the unsqueezed part of the balloon expand out. All right, combined gas law. Now, there's not a real-life example on this one. That's why that part's blacked out, so don't worry about this. So the relationships described between Boyle's law and Charles' law can be described in a single gas law. So your description of your combined gas law is going to be the relationship among temperature, volume, and pressure of a gas when the number of particles is kept constant. So your formula is P1 times V1 over T1. So your initial pressure, volume, and temperature equals P2 times V2 divided by T2. So your final pressure, volume, and temperature. So now we're going to do some examples of this. I've already manipulated the formulas for you, so I'm going to go ahead and pull up that assignment. Okay, guys, so I've pulled up your gas laws practice assignment. So I'm going to go through the examples with you. These are the examples that are worked out in the other set of slides as well, but I'm going to show you how we'd work them out. So what we're going to do is we're going to identify our different variables and then plug them into where they are in the formulas and do the multiplication division to solve for them. So the first one says a 600 milliliter sample of nitrogen is heated from 27 degrees Celsius to 77 degrees Celsius at constant pressure. What is the final volume? Remember to first convert degrees Celsius to Kelvin. So I'm going to do 27 degrees Celsius. It's my initial temperature. And it's heated from that to 77 degrees Celsius. So that's my final temperature. I add 273 to 27. That gives me 300 Kelvin. 77 plus 273 gives me 350 Kelvin. So now that I have my temperatures, I can plug things in. So 600 milliliters is my initial volume, so that's my V1. My T2 is 350 Kelvin. And my T1 was 300 Kelvin. So now I'm going to multiply 600 times 350 and then divide by 300. So 600 times 350 divided by 300. And that's going to give me 700, and then it's a volume, so I'm going to use milliliters. All right, the next one says a 250 milliliter sample of gas is reduced to a volume of 125 milliliters. If the initial temperature is 215 Kelvin, what is the final temperature in Kelvin? So it tells me my initial temperature is 215 Kelvin, that's T1. It says my volume is reduced, so that's going to be my volume 2. And then I have my original volume of 250 milliliters. All right, so I'm going to do 215 times 125 divided by 250. And that's going to give me my T2, which is 107.5 Kelvin, because it's a temperature, so it's going to be Kelvin. So now we're going to do my Boyle's laws examples. It says a balloon with a volume of 2 liters is filled with a gas at 3 atmospheres. If the pressure is reduced to 0.5 atmospheres without a change in temperature, what would be the volume of the balloon? So my initial pressure is 3 atmospheres. Atmospheres is ATM. And then I have an additional volume of 2 liters. My final pressure is 0.5 atmospheres. It says reduced to, so I'm going to do 3 times 2 divided by 0.5, which is 12. And then it's a volume, so it's going to be liters. All right, and then my final Boyle's law example says a balloon with a pressure of 4.5 atmospheres is reduced in volume from 3 liters to 1.25 liters. What is the new pressure of the balloon? So my initial pressure was 4.5 atmospheres. My initial volume was 3 liters. And my final volume is 1.25 liters. So I'm going to do 4.5 times 3 divided by 1.25. And that'll give me my final pressure of 10.8 atmospheres. So that's how you do those examples. So on this assignment, you're just plugging in your numbers to your formulas. Read through the problem, see what your initial pressure is, see what your initial volume is. Generally in the problem, the first pressure written is your initial pressure. The first volume written is your initial volume. You're just going to plug it in. Try to match up your units. You're going to round to 2 decimal places if you need to. If you need to change a temperature to Kelvin, I've included those boxes for you, like on number 5. You have to change your initial and your final temperature. One of them, you only have to change your initial temperature. So that would be number 6. All right, if you have any questions, you can message me. You're going to do great. I'll see you guys when I see you. Bye.